Hello everyone. Today we are going to study the elastic collision in the center of mass frame. Here we are dealing with the non-relativistic case, that is the velocity is much less than the speed of light. And the subheading of this topic is that through this discussion we can find out the relation between the kinetic energies in the center of mass frame and the laboratory frame. So, just a quick revision, we are already aware what the reduced mass of a particle is, what the center of mass frame is. So, when we consider collision, so in the simplest case, we will consider collision of two particles of masses m1 and m2. If we consider the laboratory frame, we consider that one of the particles, let us say the particle which is having mass m2 is at rest, and the particle which has mass m1 is moving with the velocity v1. So just a notation which we are going to introduce is that we will denote the center of mass frame with the letter capital C and the laboratory frame with the symbol of capital L, which is the laboratory frame, and C will represent the center of mass frame. In the center of mass frame, we deal with the reduced mass, which is defined as 1 upon mu is equal to 1 upon m1 plus 1 upon m2, which implies that mu will be equal to m1 m2 divided by m1 plus m2. Now let us consider that the velocity and the momenta in the center of mass system is velocity and momentum are defined here as by the letters capital V and capital P, whereas in the laboratory system the velocity and momenta are defined by small v and small p. Now, when we talk about the energies and the scattering angles in the C system, the energies and scattering angles will be represented by E and theta, which is for energy and scattering angle, whereas for the laboratory system the energy will be represented by epsilon and the scattering angle will be represented by phi. So this is the same for the same parameter we are using two different symbols in the center of mass frame as well as in the laboratory frame. So now what we want to do is we want to calculate the kinetic energy in the center of mass system, and we want to calculate the kinetic energy in the laboratory system, which is already known. We don't have to calculate it actually, because the laboratory frame is the real frame in which the scattering is actually happening, and when we want to study it in the center of mass frame, we deal with the reduced masses and the energies and velocities which change as according to the relations which we are going to study. So we already know that in the laboratory system, as I already showed, that this is the laboratory system, and in the laboratory system the mass m2 is at rest, so the velocity of the particle in the laboratory system, that is small v2, is already equal to 0. Okay, so now if you want to define, let us write here now the velocity of the center of mass in the lab frame is given by, we already know this relation, Vc is equal to m1 v1 plus m2 v2 divided by m1 plus m2, where we already know that v1 and v2 are the velocities of the masses m1 and m2 in the lab frame. Let us mention that also here, said that v1 and v2 are velocities of m1 and m2 in L frame. Okay, now we know that since m2 is at rest, therefore v2 is equal to 0. Therefore our vc becomes m1 v1 over m1 plus m2. Okay, so now if we want to define the velocities of, now we define the velocities of masses m1 and m2 in the C system. So we already know what formula are we going to use. The formula which we are going to use will be V1, which is capital V1 is equal to small v1 minus of Vc, which will be equal to m2 v1 over m1 plus m2. You can also deduce this formula using this relation which we have already calculated, v1 minus m1 v1 over m1 plus m2, and when you solve this you will get m2 v1 over m1 plus m2. So you can use the above relation, which is this relation. Let us name it equation 1. Let us name this equation as equation 2. Now let us define capital V2 also for this. Let me use a proper notation. Capital V2 will be equal to nothing but V2 minus Vc, which will be equal to minus of m1 v1 over m1 plus m2. This is our equation 3. Now when we want to define the corresponding momenta, the momentum corresponding to it will be, the momentum will be P1, which will be equal to m1 v1, and P2, which will be equal to m2 v2. This is given as m1. Let us put the value of v1 and v2 from equation 2 and 3, which we will get as m1 m2 v1 over m1 plus m2, and when we write it here we get negative of m2 m1 v1 over m1 plus m2. Now as you know that from the equation of reduced mass, we know that the reduced mass, which we already calculated earlier, is given by this equation, mu is equal to m1 m2 over m2 plus m1 plus m2, which is given as we find it here, this is nothing but mu times small v1, and this is negative of mu times small v1. So now as you can see that the momentum of these particles are equal in magnitude but with opposite direction. Therefore we can write the total momentum as, the total momentum will be given as P1 plus P2, which is equal to mu v1 plus of minus mu v1, which is nothing but 0. So we can see that since the initial momentum is 0, therefore by conservation of momentum, the conservation of linear momentum states that the final momentum also should be 0. States that, let us write it here, final momentum must also be equal to 0. That is, if we represent the final momentum by P1 dash plus P2 dash is equal to the initial momentum's sum, that should turn out to be 0. Okay. Now let us denote the primed value. These values are the values before collision, and the unprimed values are the values after collision. So this is just a notation that we are using. Okay, so now after we have dealt with momentum, after we have dealt with velocities, the next parameter that we want to deal with is the kinetic energies. So now we deal with the kinetic energies, so we can write the sum of kinetic energies before and after collision is given by E1 plus E2 is equal to P1 square over 2m1 plus P2 square over 2m2, and this is nothing but P1 square plus P2 square bracket 1 over m1 plus 1 over m2, and if we take out the value of 2, factor of 2 out here, we get p square over 2 mu, where we have defined p1 square plus p2 square is equal to p square. And similarly, we can define E1 primed and E2 prime as P1 prime square over twice M1 plus P2 primed square over twice M2. This will give us P primed square over 2 mu. Now, by the conservation of energy, we can say that E1 prime plus E2 prime is equal to E1 plus E2, and we know that we can also see that magnitude of P1 is equal to magnitude of P2. Let us say that it is magnitude of P, and the magnitude of P1 primed is equal to magnitude of P2 primed is equal to, let us say, magnitude of P primed. So by the conservation of energy relation, we can write that the momenta of the particles before and after collision are equal. That is, we can write P1 is equal to P2 is equal to P1 prime is equal to P2 prime. So the values which we have calculated earlier, you can find this here. So please be a little careful about the notations I am using, that these values which I have written are small p. So I have put a mark here which represents that this is small p, and the capital P do not have a tail in front of it. So yeah, so please just be careful about the notations. So now when we refer to the momentum diagram, so we are dealing with collisions, and we want to see how the particles are colliding and how are they scattering, what are the angles they are taking. So we are well aware with it. So now we are going to look at the diagram in the center of mass system. So I just want to make a quick diagram over here, and let us see how it takes place. Okay, so this is the momentum diagram which shows the collision in the center of mass frame. Just a small correction which I wanted to mention here is that the primed coordinates represent those entities which are after collision, and the unprimed for before collision. So let us make a correction over here. This represents for after collision and this represents for before collision, as we already stated. So let's move ahead, and as we have already seen that the momentum fly off opposite to each other with the same magnitude, and since the initial momentum is equal to the final momentum, so then we can write that the angles with which they fly off, that is theta 1 plus theta 2, will be equal to pi, because they fly off in just the opposite directions. So now when we want to calculate the kinetic energy of the center of mass, it is given by kinetic energy of the center of mass is given by EC. Let us use the symbol EC for it, and we will write half the total mass m1 plus m2 times the velocity square, which is vc square, and we have already defined vc square, which was vc was equal to which was equal to m1 v1 over m1 plus m2. So let us use this relation in the equation of EC. So we get EC as half of m1 plus m2 m1 v1 m1 plus m2, and since there is a square to it, so we will have to do it 2 times. Now this term will cancel out, so what we are left is with half of m1 square v1 square over m1 plus m2, and we can write this as half of m1 over m1 plus m2, and we can write this as m1 v1 square. So what we get is, now on rearranging the terms, we can write EC as EC will become m1 plus m1 over m1 plus m2 times half of m1 v1 square, and this is nothing but, this term represents the kinetic energy in the laboratory frame of the particle with mass m1, because the kinetic energy of the particle with mass m2 is 0 because it was at rest. So we can write EC as m1 over m1 plus m2 times epsilon 1, and this is the connecting relation between the kinetic energy in the center of mass frame and the laboratory frame, as we can see here. So using this method, we can reduce the, if we already are aware of the kinetic energy of the incident particle with momentum, with the known momentum and with the known velocity which we already have, we can calculate the kinetic energy of the particle in the laboratory frame, and then using this relation we can calculate the kinetic energy of the center of mass, which is given by EC. Now this energy EC, this is totally not available for the any reaction to take place when we deal with the inelastic effects. So if we want to calculate the amount of energy which is available for any reaction, let us write that also. The energy available for any reaction to take place is given by delta E. Let us use this symbol. Is given by delta E, which is nothing but E1 minus of EC, which is E1 minus of M1 over M1 plus M2 times E1, which is nothing but M2 over M1 plus M2 times E1. Okay, so if you put the value of E1 into it, what do you get? You will get M2 over M1 plus M2 times half of M1 V1 square, and on rearranging the terms we can get M1 M2 over M1 plus M2 times v1 square, and this can be written as half of mu v1 square. So this is the extra energy available for any reaction to take place. So from all these discussions we can see that there is no change in the kinetic energies. So in conclusion we can write what we can write, that the kinetic energies remain unchanged. Kinetic energies remain unchanged before and after collision. As well as the momentum of the particles P remains unchanged. So thank you for your time, and do let me know if there is any doubt or any confusion in the comment section. As for the notes, these notes will be available to you, and I have already posted the link of the notes in the description box. So see you for the next video. Thank you.